Monte Carlo. So first I'd like to say that this is actually derived work on a master thesis I did with Joakim about a year ago, supervised by Ken. And the thing we did was we developed a domain-specific language embedded in Haskell for expressing stochastic processes. And the reason why we did this was because we want to express the price of financial contracts, and also to be able to simulate this price. So what we present today is a newer version of this language that is more explicit about what is stochastic and what is not. So yeah, we can do it. So if you want to go home and trade financial contracts on financial markets, you should probably know what you would expect the prices to be, or the value of them to be, because it's not certain in the present, because they depend on stocks. That is, it depends on the future, of course. So what the domain experts do is they usually model this using stochastic processes. And they incorporate something they call a financial model into it that describes real-life stuff, such as interest rate and so. And it also describes in terms of stochastic processes. There's also been an approach, it's more than 10 years old, by Simon Peeling, Jones, and 2 other guys. They made another DSL, also embedded in Haskell, for describing contracts composably, often informally. And in fact, we wanted actually to start to target this language, but we ended up that they're not perfectly fit for each other, because we can't really price Asian options today, and composable contracts do not support parse dependencies as we do. But we'll see that. So, oh yeah. Sorry about that. So, my point is that stochastic processes are quite crucial here, and you want to be able to, at a certain point for these processes, to estimate the value, because that's the price if they're modeling a contract. So you take your favorite numerical method and language, and you can do it. But every time that if you want to do this for a new contract, you have to do it over again. So we thought it would be good to have a language for this. And this is SQL. And along with SQL, we also implemented a backend that runs a Monte Carlo simulation, and it runs via OpenCL on graphic cards. So let's start by an example. So a nation offset with floating strikes. This contract gives the owner of the contract the option to buy a specific stock at a specific time in the future. And so at that time, the owner can choose to exercise the option, and if she does, she'll have to pay the average price between the initial time and the exercise time. So what is the value of this? What is the price of this? And if we ask the domain experts, they'll probably give an answer like this. And so let's look into it. What they do, they start by defining a Brownian motion, they call it, that is a stochastic process. They use to capture the uncertainties in the underlying of the stocks. And this notion, so this V is a function from time to distribution, or random variable. So 0 is a time 0, we have the random variable that is certain to be 0. At any point later than t, delta time later than t, we define it to be value at t plus the normal distribution and the square root of delta time. So notice here that this plus is between normal values, between distributions. It's not simple arithmetic on real values. No, that's classic notation. And then you can look up this formula in a textbook, and I'm not going to the reason behind it, let's leave that to the domain experts. But that's a model for given these 3 constants, the initial value, the interest rate, and the supposed volatility. They give this expression for an underlying. And with this in hand, we can model the process describing the price of the contract. And this is more clear what the reason is here. The max 0 is because you don't have to exercise, so the value can never be 0 or negative. And here is you receive the value of the stock that you buy, and this is the price you will have to pay. You subtract that. And you use the average. This is the running average on the underline from initial time to t. And this is the discounting factor. So we have the model built into this one already. So let's try to picture this. So this up here is just a random trace from the Brownian motion. You can see it starts at 0 and it's quite lively. It goes up and down. So having this trace, let's try to build a trace for the stock. So in this case, S is 0.8, and you can see they are clearly related. And the average, we take the average on the underline, and this is the running average on the blue one. You can see like this. And now we can describe the price process. And first you can see whenever the average is below the stock price, you'll get a positive payoff. And it's always at least 0 because of the max 0. The discounting is hard to see because in this example it's 5%. So this is the price at time 1. But this is not the whole picture, right? Because it was just one experiment. So the Monte Carlo method, the method there is to just do this a lot of times and to take the average. And that is the approach we're doing because it's really easy. But this was the mathematical definition. Let's try to see what it looks like in SQL. But there's first a little thing, we don't have the normal distribution in SQL. But we do have the uniform distribution, and we can construct the normal distribution using the Box-Miller. Let's note this notation they use, the mathematicians use indexes here to denote that these are unrelated and independent uniform distributions. And this is important. So, this is what it looks like in SQL, at least the new version here. And there's a lot of things to know. First, we're in a do block. So this is obviously some kind of monad. And for those of you who have read the article by Martin Ervik on the probabilistic function programming, this is exactly what he's doing. Making this probability monad. And what we're doing is that we are sampling from so the bind is sampled. So we take a stochastic value into, in this case, a real value between 0 and 1, and then we can use it twice. So this is a non-stochastic expression, and we return it and yield something that is again stochastic. But compared to PFP, you should know that this is, first of all, this is symbolic. You know, I've already told you that we compile it into OpenCL code, so we can refile this. Another thing to note is that we have uniform, continuous sample space. This is not a list, and we're not sampling right away. This is continuous between 0 and 1, and so normal is continuous as well. So with this normal in hand, we can define Brownian, and this is a inductive definition, and so is ours. So we use the built-in construct iterate, and we start with a base case, like up here, and then we give a function that, given the value at time t, will construct the value that is delta time later. And this is exactly as what we're doing up here. But it's different because we cannot really make it a pretty one-liner, because we don't want to have the n, that is the normal distribution, just put it in here, or in here. We did that in the old one, but we'd like now to be more distinct whenever something is stochastic and not. So we do it like this. So with this normal, we can build the underline, and we do this as a function from, take the tree constants. And now we sample from the Brownian motion. So this is not a real value anymore. In fact, but it is not stochastic, but it's a function from time to a real value. And then we define u, like up here, but u is not as the process, u is a trace. like this one, we call this a trace as well. And we define it like here, just with Haskell notation for the parentheses. And this is not a process, this is a trace. But then we return you, and we get a process. So the last piece, remember we had the array. We needed that, the running array. And for this we use the scan. This is pretty much like scan in Haskell. It's just not on list, but on functions. And the way we compute the running array is that we first construct the trace of pairs that has sums in the first part, the accumulated sum in the first part, and then the count in the second one, and then we look up time t, and we divide it. So now we can construct finally our Asian price process. So first, we sample from the underline, as we cannot use it directly. As up here, they use it directly. We do not. And then we define price similar to A, and do the Haskell style of this one. And then we return price like before. And that's it. So let's imagine that we are in GHC I now, and we're doing some experiments, and we just define the Asian, and then we use compile to, this is a process of real, this expression here, we compile it, and what it does, it will reify the syntax tree, transform it into OpenCL code, compile it with OpenCL, and then load the kernel into the devices available, and then, yeah, that's a side effect, and then it returns a function that you can call. And now we decide on, we need to discretize. So now we decide on what would we like our delta time to be, and we choose this, approximately a day. And yeah, time is measured in years. And then we can call it, and it will run whatever count. This is, I think, 1 million. It could be more. It doesn't matter. It's not live. But we can do it several times. But to compile and load this kernel takes several hundred milliseconds. So we would like to not do it all the time. So we can make the kernel more parametric by not giving the arguments already, but delaying them for when we invoke the kernel. So we can load a kernel that can handle a lot of Asian options. And yeah, if we work through that.
So what we just saw was a composition of stochastic processes that could then be compiled to OpenCL code. And the reason that it was so easy to compose these is that they really have a direct correspondence to the mathematical notation. In particular, we don't concern ourselves with the choice of distribution. I don't mean distribution, but discretization. And we don't concern ourselves with when does this process end the infinite. And yeah, so in order to take this specification and compile it, we need it to be symbolic, as Mike said. So our two core types, sample and dist, are actually syntax tree in behind the scenes. And we will load plus to generate a syntax tree and so on. So sample is our non-stochastic values, and dist is our distributions. And then we have the trace that goes from time to value. And our processes are distributions of traces, which is a little bit different from the probabilistic functional programming article, which has traces of distributions. And these are really dual, you can do both things. But we do this so that when we use bind in our monad, we get a trace out for process. So and here is our syntax tree. So up here we have Boolean values, and we have an if statement, And then we have real values and arithmetic on that. And we have pairs and first and second. And we have the scan that we've already seen, that is similar to the Haskell scan, but just in traces. And for distributions, we have the uniform distribution, which is the only source of randomness that we have. And then we have the iterate that builds up processes by an initial value and a step function, like we saw in the browser in motion. And then we want to make it a monad, but we have a problem because this type variable out here is it's bare. It could be anything, and we can't verify anything. We can only verify our own types. So we need to put a constraint on this type variable that says I only want my own types here. In order to do this, we use restricted monads that lets us do this, because normal monads don't. So now we have a high-level specification, and we want to compile it and execute it. And this is the time where we choose our discretization and our end time and so on. So if we take an example and average over some trace at time 7, if we want the expected value for that, then we need to discretize the time. That is, we choose a number of time steps, delta time, and discretize the real numbers as double precision floating time values. And then let's look at a single simulation. So one thing that we could do is to compute the values for the trace and store that in an array, and then compute the values for the average. Now that we have all the values that we need up here, but then we're going to store this array in memory. And since we're working on the GPU, which has a lot of processes, we don't really want to allocate a big array on every process, because that's going to, or threads, but that's going to consume too much memory. So instead, we compute all the values at time 0, because when we have the value at time 0 for our trace, then we can compute the value of our average at time 0. And when we have that, then we compute the values for time 1, and so on and so forth, until we get the desired value down here. And as you can see, the only thing we need to store is the accumulator of variables and no arrays. So for Asian options like we saw, or at least this instance, they're simply Markov processes, and in that case we can our runtime complexity is simply the number of time steps that we need to take, as was evident from the example I just showed. So the code we generate is simply for this case at least, is simply a for loop that iterates over all the time steps and updates the accumulator variable. So now that we have the OpenCL code, we'll run one simulation per thread. Every thread gets its own seed, so it can generate different traces. And then at the end, we execute another kernel that takes the average of all the results of each thread. So in the simulation, we just use variables and no dynamic allocation or arrays. And since Monte Carlo is embarrassingly parallel, and our simulations don't have to communicate due to that, we expect that executing n simulation on one multiprocessor and executing k times n simulations on k multiprocessors should take the same amount of time. And indeed, when we benchmark it, that's what we get. So this is a time in milliseconds up here, and the number of work groups over here. And a work group is a pool of jobs that is executed on one multiprocessor, on a GPU, no cell. And we have 40 multiprocessors. And then what we can see is that as long as when we have we use 7 multiprocessors to compute 7 times 512 jobs over here. That takes the same time as using 40 multiprocessors to compute 14 times 512 jobs over here. So it's we can expect that if we increase the number of multiprocessors, then this will be flat. And we can so it subscales. And the reason that it goes up here is that we run out of multiprocessors, and now we have too many groups, so they wait in line to be executed. It's flat again, and then we get to the next modulo 14, and it jumps up here. And then we benchmark it against a handwritten C implementation that does the same thing but sequentially. And what we get is a speed of about 100, which is useful. Yeah. So I think that was about it.
Any questions?
I have several questions, but let's start with the simplest one. So domain experts know that the price can jump sometimes. And the simplest stochastic process which have jumps is the Poisson process. So can you do Poisson processes with this framework? Poisson process. Can you do the Poisson process?
It looks like Ken would like to work on that.
The answer is yes.
Then can you do Poisson process with stochastic jump rate?
We can, if you have a function that can generate your distribution, can generate a graph, then we can model it.
Yeah, but the question is, can you encode this function with this framework?
Yeah.
Or like Levy process with stochastic parameters, stuff like this.
Again, if you can write it up as a simple mathematical formula, then yes, we can have it.
Maybe I should take this offline, but I'm not sure you can encode it then. Okay, and another question is, what is the reason not to include, say, normal distribution directly as a primitive?
It's just a matter of minimalism, really. Could do that.
Mm-hmm. Okay.
And the way we did implement it is actually it's a Box-Müller transform, but we only use one of the results.
Yeah, but I think that's not the most efficient way to
no.
do it. Okay.
That's easy to change.
Anybody else? I gotta go. Steve, local organizer?
Has a simple question. First of all, it's fascinating that you're actually pursuing specifying stochastic processes and deferring the fixing of the discretization until the very end, indeed after you've generated the GPU code. If I understand right, you have parameterized over the delta t.
Yeah.
So it gets passed in at runtime.
Yeah.
The question is, if you knew it were a constant, don't you give up on some numeric optimizations that you could perform if you had put it in beforehand? In other words, is the way of specializing the code to certain delta t's, certain discretizations
So
would you expect any benefit from that?
So the answer is that in our old implementation, you could choose whether this was a parameter or not simply by making it around to the. Actually, no, you couldn't do that. No, you can only do it all the time. But in actually our compiler is pretty simple, so we would leave that kind of optimization to the open shell compiler, which may or may not be smart enough to do it. And our compilation step is very simple. We just generate this values. So there's not a lot of optimization beyond the function.
So to supplement that answer, yes, we could definitely gain some benefits, some numerical optimization by actually having more control over the discretization. The reason why we left out is simply because we had to stop. There's plenty of knobs you can turn. This is one, and we were sort of just happy to get all the way through with so we have made many sort of just taking a simple choice and then sort of try to identify the most promising knobs to then try to turn. But yes, the translation, discretization is and the optimization related to that. That sort of, we can either do that in our compilation, or we can do as Joakim say, leave it to the OpenCL compiler and notice that here's actually some constant expression which could be lifted or could be simplified. And then by us not doing it, then we'll not be the one fucking up the floating point arithmetic. So that could be another reason for not doing it.
You've been screwing up.
We are being videotaped. Well, my question was, I'm very interested in how you did the GPU code generation. And in particular, I'm wondering what it would have taken for something like Nicola or Accelerate to have been able to help you out with that and not maybe go all the way down to OpenCL.
All the way. So actually, we spent more than a month trying to do it with Accelerate or Nicola, and that's 1.5 years past. And at that time, we had really hard to get it working with these libraries. I think it would be easier today. But a thing to note is that we would like to do the deep embedding on our own anyway, because we like to have SQL as a specification. And I think that's actually in this implementation, this is the hardest part, is the deep embedding. It's not the OpenCL code generation.
Oh, okay, interesting. Well, let's thank our speakers again. Oh, sorry, there's a question. Unthank.
I might as well take this one. I understand that you discretize very late over time, and that it's a continuous process that you model. But what are your numeric types that you can model? So it's actually also related to the code generator, because you need to generate code for data types that are supported.
So the real numbers are modeled as double precision floating point values, and apart from that, we just have Boolean values and pairs. So the trick is.
Would it be easy to expand that to integers, which would model then a discrete distribution?
Yeah.